Okay, so thank you very much for the opportunity to speak at this workshop. So I will talk about the project Charmonium and Confinement from Lattice QCD at SuperMUC-NG, and my collaborators are Roman Höllwieser, Tomasz Korszec, and Juan Andres Urrea Nino from Wuppertal, and Mike Peardon from Trinity College in Dublin. The results that I'm going to present are part of the research program of the research unit, Future Methods for Studying Confined Gluons in QCD. I'm the spokesperson of this research unit, which is funded by the German Research Foundation, and the partner institutions are Wuppertal, Zeuthen, and Trinity College, Dublin. So the results that I'm going to present here, which have been produced at LRZ, they are part of the goals of the research unit. In particular, I will highlight today the computation of the Charmonium spectrum and of difficult contribution called disconnected contributions. Then I'll show some result on the static potential. And I will also show some development that we have on a more algorithmic side in the connection of with multigrid methods for linear systems. So the outline, I'll give a brief introduction to Lattice QCD, and then I'll talk about hadron spectroscopy in connection with a technique called distillation, and show results about the Charmonium spectrum and potential. So to set the stage, this project is about investigation of the strong force. The strong force is responsible for the interaction between the elementary particles, quarks, and gluons. The peculiarity of the strong force is that it confines, it binds these elementary constituents into bound states. And so we are never observing actually quarks and gluon, but what we see in experiments are hadrons like proton, neutron, and pions, etc. And the strong force is also then responsible for binding the nucleons into forming the atomic nuclei. The fundamental theory that describes the strong force is called quantum chromodynamics. And to put it a bit into the bigger picture of all elementary particles in what is called the standard model of elementary particles, I show these slides. We are concerning here in the study of the quarks and their interaction via gluons. So we are focusing on mesonic states, which are states made of a quark and an anti-quark. For example, an up quark and an anti-d quark, they form what we call a pion. And in our project, we focus on states that are made of a charm quark and the charm anti-quark, which are called Charmonium states. There are further possibilities. If one puts three quarks together, one gets baryons. And there are also, and there are further states that can exist. For example, states that are made of pure gluons. And this is this picture on the bottom right, and these are called gluons. So how do we compute the properties of bound states in quantum chromodynamics? Well, the methods to go for this calculation are numerical simulation of the theory of strong interaction through Monte Carlo methods. So what one does, one discretizes, first of all, the theory on a finite space-time lattice. This lattice is Euclidean. It's a hypercubic lattice with a lattice spacing that we call A. The carrier of the strong interaction, the gluon, they sits on the links which connects to nearby points on the lattice. These are these green arrows that you see here. These are the gluons. And the quark fields, they are actually anti-commuting variables which sit on the on the points of the lattice, represented by these purple points here. And then there are the interaction between quark fields is described, for example, by covariant derivatives of the quark fields, where then the gluon comes into place. In order to compute the properties of the theory, we need an action in terms of the quark fields and the gluon fields. And in particular, for the quark fields, what appears in the action is a Dirac operator, which becomes a large matrix if we discretize space-time. So once we have the lattice and the fields and the action, then in order to compute the properties, we do this via Monte Carlo method. So we do statistical simulation. We create a configuration of gluons drawn with the probability given by Boltzmann factor with the action in the exponent. And typically we have thousands of such gauge configuration in one ensemble. And then we perform ensemble averages to compute different observables. The observables that we will be concerned today are correlation function that describe the propagation of mesons in time. And this propagation is described by quark propagators. Quark propagators, this is the central computational task that we perform on SuperMUC. Quark propagators, they are solution of the Dirac equation. So the Dirac operator times the quark propagator is equal to a source, which I call here VI. And this is the most intensive part computationally. And this Dirac operator D is a matrix which has size of 190 million, and it is though a sparse matrix. Therefore, in order to solve the Dirac equation, we employ highly optimized algorithms. And the peculiarity of our study here that I'm presenting is that the right-hand sides, these VI, they are eigenvectors of the three-dimensional Laplacian operator. This is what is underlying this technique called distillation. And when we talk about quark propagators in this context, we actually mean quark perambulators, which are dot products of the eigenvector with the solution of the Dirac equation. So today I'll focus on a gauge ensemble that has been generated, including 3 light quarks. They correspond to up, down, and strange in nature, but they are not exactly like in nature. They are degenerate while they aren't in nature. But the sum of these of their quark masses is the same as in nature. And in addition, we have a 4th quark, dynamical, which is a physical charm quark. And we are particularly interested in the Charmonium states, and therefore we have a physical charm here. The lattice, where most results will be have been generated as size 144 in time times 48 in space, 48 cubed then. It is a quite fine lattice spacing which is needed for these studies. And we want to compute the masses, the energy levels of Charmonium, and they are typically labeled by the total angular momentum J, the parity P, and the charge conjugation C. And the computation, we do them with a measurement code called QCD that has been written by us in C and MPI. So here it's an example of how we extract the masses of Charmonium, so the energy levels. So we compute the so-called effective masses. They plateau, so the effective masses are a function of time, the separation between a source and the sink, and the plateau of the effective masses is what we call the particle energy. And here are few examples for Charmonium states. So the dots are the effective masses that one gets with standard distillation. And we have developed an optimized version of distillation, which are the pluses. And one clearly see that the pluses are much flatter than the points, indicating that we can extract the masses of the particle at earlier times, which is quite crucial for our project. On the right, this diagram that you see here shows the masses that have been measured in nature. These are the black lines in these diagrams. So what I will focus here are the 8 low-lying states of charmonium, eta C, J psi, and etc. So there are 8 states which are stable because they can't decay strongly. But the interest in the system, of course, comes also from states above threshold. And in particular, these red states marked here, they have been quite exciting for our field, and they await from a theoretical explanation. So as a further motivation for what we do. So now here one sees on the plot, in the plot on the left, our lattice results, and they are, you can compare them with the particle in nature on the right. And what I display in the left plot are in black, these are the particle masses that we extract, indicating only the statistical error. And you see that we have quite precise determination. But then we have to include a further error coming from the overall energy scale on the lattice, and this gives this light shaded gray bands. And in blue, we compare with the values in nature of these low-lying states, and we find very good agreement. What we can do with this technique of distillation is also to get the footprint of these mesons. So, and this is what we see here. This is the wave function in space of these mesons. The upper 2 plots show the ground state and the first excited state of the eta C particle, and the lower 2 plots ground and first excited state of a charmonium where the 2 quarks have an orbital angular momentum equal to 1. And these plots are nice because they show that we also get orbitals, right? Like for atoms, for these particles. And they also show that our boxes are big enough to contain the states. One uncertainty which is left in lattice determination of charmonium comes from so-called charm annihilation contribution. So not only the meson can propagate, but we can also have a contribution that comes from the annihilation of charm and anti-charm at source and sink. And this contribution are on one side suppressed by what is called the OZI rule, but on the other hand, this rule is not quantitatively well understood, and it is important to include them and really verify at which level they contribute. And in fact, in a model study, we can detect how the mass of charmonium state shift when this charm annihilation contribution are included. And this is a first step towards determining them in a more physical setting. This is the difference between the red crosses and the green points in the plot. And it gives the shift due to the charm annihilation. Another thing that we can do on the lattice is to connect the levels of the energy levels of charmonium with a quantity called the static potential. The static potential is a central quantity to study confinement, which is at the core of the theory of strong interaction. And confinement manifests itself by a potential between quark and anti-quark, which rises linearly with the distance. And this typically is shown as a flux tube. You see a picture here on the right. There is a flux tube that confines the quark and the anti-quark. The more we separate the quark and the anti-quark, the more energy there is in this flux tube, and eventually this flux tube breaks There is a so-called string breaking phenomenon, which we will study in future. But also here, we are developing new techniques to measure this potential, and we can extract, you see on the left, in blue, the ground state, in red, the first excited state, and in purple, the second excited state of these potential levels. Finally, I'd like to show something about the performance and the scaling on SuperMUC. So on the left, there is a scaling plot, so the speed up for the solution of the Dirac equation for a lattice which is 96 times 48 cube with a GCR algorithm using publicly available software OpenQCD. And so we start with 16 nodes or 768 cores, and then we divide our lattice into more and more cores. And the red line is the ideal speed up, and one sees that up to 6,000 core, our code is performing well. Recently, we also have implemented another highly optimized solver, which is the multi-grid solver DD alpha AMG. This is a 3-level, truly multi-grid solver. And the plot on the right shows the time to solution as a function of the number of nodes used. And the OpenQCD, so the solver that you see on the left, are the blue points. The circle are for the heavy quark, and the squares are for the light quarks. And in red, we compare the time to solution using the multi-grid solver. And again, the red circles are for the heavy quark, and there we don't gain with respect to the blue circle. But for the light quark, which is the more expensive, you see that the red squares, as we increase the number of nodes, they get more and more efficient. So we benefit from a truly multi-grid. And now I'm about to conclude. So what I have presented here are results essentially on the improved Charmonium spectrum and static potential using our improved distillation technique on a set of gauge configurations that are very close to nature. And the outlook is we want to include now also the propagation of light quarks into these studies, and the inversions here are much more expensive. And therefore, we will start with a smaller lattice where we can afford the larger statistics, and we will study the mixing of Charmonium states with light hadrons and blue ball states, and also other mesons like D mesons and hybrid potentials. And of course, it is essential, which is also at the core of the research unit, to develop further numerical methods, and we are working on multi-grid and GPU codes. I thank you for your attention.